listening. Let's open up our booklets now, and we're going to talk about the periodic table, which starts on the bottom of page 6. And we're looking more at not the physical size of the elements, but their chemical properties. That's what we're interested in for Criterion 7. I'd also like you to pull out your formula sheets so that you can be looking at the periodic table. Alright, so let me open to this page here. Yeah, the periodic table. The ones that we need to be focused on, group 1. What's the name for our elements in group 1? Alkali metals. So it's group 1 with an Arabic numeral, the ones we normally use for counting, and it's also group 1 in Roman numerals. And our first alkali metal, lithium, sodium, potassium, etc. Yeah, so hopefully you can find all of these on your periodic table. What about hydrogen? Is hydrogen a group 1 metal? No. Even though it's sitting in that position on the periodic table that you have on your formula sheets, it is not a group 1 metal. The first group 1 metal is lithium. So we have rubidium, cesium and francium rounding out group 1. We don't really look much past there, but hopefully you would be able to find them. And you would know that they all share a similar characteristic. And what is the characteristic that they all share? They all have one valence electron. How do they all react? Yeah, so they all react by So if we think of this as a before and after, what would if this is a before reaction, what would I write then for each of these elements after they've reacted? Positive 1. Now, I guess we should note that francium being radioactive, we really don't, the chemistry is, as I said before, it's clouded by its radioactivity. So we're putting it in here as a trend for group 1 metals, but we would never really look at reactions of francium for that reason. Now, what else can you tell me about these group 1 metals? What's another property that you know of them?
That they're one of the most reactive elements.
Yeah, so they're very reactive. And they'll react with air and water, won't they? So they all aren't identical in their reactivity. How can we describe the trend of reactivity?
Increases
Okay, so we've got increasing reactivity. And that's right, because increased distance of the valence electron from the nucleus. Okay, and which more shells. Yeah, got that. And as we add another layer of electrons in, so that our valence electrons then become further away from the nucleus, they're less firmly held by the nucleus and they're easier to lose. And the other reason, there's another reason why they're
shielding from the inner electron.
yes. Okay, same thing. Those more shells have also led to shielding, so that the pull of the nucleus on that valence electron has to pull through those inner layers of electrons, so it's more difficult. Okay, if we look at our next group that we need to consider for fissile, that is group 2. Which is also the Roman numeral 2. And what's group 2's name?
Yeah.
What is it? What's our first metal in group 2? Computer. Is there a beryllium sphere on board? I love Galaxy Quest.
What did you say?
Where their spaceship is powered by a beryllium sphere. Yeah, it's pretty cool. What's next? Yeah?
Calcium, strontium.
Yep, so they're our group 2 metals. And yeah, we can think, can't we, about the same sorts of things as we looked at for our group 1 metals. After a reaction, what are we going to form? Oh, actually, let's finish off this bit here. What do they all have in common?
They all have 2 valence electrons.
And how do they react? If they're going to donate by how many, can they react by donating one of those electrons?
No, because they won't. Yeah.
That's right, they have to donate both to be stable.
Yeah.
Yep. So that means that if we looked at what they're going to look like after they react, about the reactivity trend, or how reactive, just as a statement, how reactive are they in comparison to the group 1 metals? Is that
Not as reactive.
not as reactive? but still pretty reactive. So if we call those ones very reactive, we'll call these ones reactive. Why are they less reactive than the group 1 metals?
Because they have to, I guess, lose the 2 electrons rather than
Yes.
1 has to lose the
So it's a little bit harder to lose 2 electrons than it is to lose 1. So also the electrons are attracted more to the nucleus. It's a smaller radius, so those electrons are closer to the nucleus. What about the trend for reactivity? What's the direction of the trend for reactivity? Down? Still the same direction. Why would it be the same?
because it's still giving up electrons instead of taking it.
Yeah, so the reasoning works the same as it did over here, because we're still talking about reacting by losing electrons, and we know that as we go down the group we've got more and more shells, and so therefore those valence electrons are further from the nucleus. So yeah, that reasoning works for this. Now, what else is it about them? We've called them metals. These are metals. What else is it that we know about metals as far as the way they react? How do metals react?
They only bond ion.
Which means if they're only bonding ionically, what can that tell you about what has happened in the process of a chemical reaction? If I started out with a metal and I reacted it with something, and then I formed an ionic substance, what's the state of the metal in the ionic substance?
Is it a salt?
Well, this is called a salt, yeah. But I want to know something more about the metal itself. What form is the metal in? It's always a cation. Okay, so the metal will have a positive charge because it always reacts by donating electrons. That's what metals do. Now we're calling some things that would maybe categorise as metalloids. We're just calling them metals because we don't want to have too many divisions on our periodic table. So we're just saying it as a metal. That's how they react, by donating electrons. And we could see that evident in these two groups, but it would be the case for any of the metals on the periodic table that we haven't considered either. So you're not going to, if I just pick on manganese there, right in the middle, in the transition metals, there, okay, it's never going to form that, okay? It's never going to form a negatively charged ion, because it doesn't react by accepting electrons. All right, so our metals react by donating electrons. Now, in our analysis of our groups, we then skip all the way over to the other side of the periodic table, and we look at the halogens. So what I'm going to do, I'm just going to get rid of the alkaline earth metals, and I'm going to put the halogens here. Right, so we're up to now, this is group 17. Which is group 7 with Roman numerals. And there was a question about group 17 on the test. I've already called them halogens a few times, so no prize for calling them halogens. And if we look here, we've got fluorine, chlorine, bromine, iodine, astatine, and after a reaction, firstly, tell me what they all have in common.
They all?
Sorry? Yep.
They all have 7 valence electrons.
They all have, oops, wrong colour.
She looks like a good girl.
Now these ones can react because there's another way for them to react. So this is just one way. By what? By, yep, so gaining 1 electron. What does that mean the valency of the halogens is? 1. Because valency is talking about how many bonds can you make. So it has 7 valence electrons, but it can only form 1 bond. So therefore it has a valency of 1. Now, if we're reacting them in this way, if we're reacting with a metal, what does that look like then over here? Yeah, all minus 1. And if we consider also the reactivity trend for group 17, and if I have my arrow pointing in the direction of increasing reactivity, which direction do I need to point? Up. Why is the reactivity increasing going up group?
Sorry, because it has a small size, so the protons are able to attract the electron easily.
Yeah. So here it's the same reasoning, but because we're attracting electrons rather than donating electrons, the attractive force from the nucleus is greatest when the atom is small compared to when it is bigger. So the reasoning is the same. Yeah. So we have lower reactivity down the bottom of group 17 because of the increased distance of the valence electrons from the nucleus and the shielding of the inner electrons, and it's more difficult for the nucleus to attract an electron. Okay, and then we also need to think about group 18 and group 18, what are they called? Noble gases. What do we think the state of all of our elements in group 18 is? Gas. They're all gases because they're all called noble gases. Yep. And we've got, let's make sure I've got them right. Helium, neon, argon, krypton, xenon, radon, argon, neon. Alrighty. How about these ones for reactions? Well, they have no valence electrons, do they? So they're all stable, unreactive, full valence shell. We can force some reactions, but by and large, they're very unreactive. All right. What about their? That's all right. The physical trend is really criterion 4. So hopefully most of that is a bit of a recap